Okay, so another thing that I want to demonstrate is that in the CodePeer report, we have a lot of control over here. And we've added a whole new section for CWE. So if you know your CWE identifiers, at some point we'll have a little mnemonics here to give you a little hint. But right now we're presuming that you're a real CWE expert and you're interested in only certain CWE checks. So let's turn off everything else. We'll just now be depending on CWE identifiers. And let's turn all those off as well. And now we're interested in only one. And 118, turns out that has to do with numeric range checks. And so for focusing on that particular CWE issue, then we've now going to only have that message. Let's try another one. 124, I happen to know, has to do with array indexing. And so here we end up with two messages, both relating to array indexing. One is the numForks check here, and this is also a similar check having to do with the number of forks. So this gives you nice control if you want to use CWE identifiers, and you can turn them all back on, all off, and so on. We also have, so let's get rid of the CWE identifiers and let's start thinking about some of these. These are essentially different kinds of runtime checks in Ada, and we can focus, let's say, just on access checks. That's the one we want to focus on right now. So we'll turn off all the others. Oh, I'm having a little trouble doing that. Turn them all off, and let's just turn on the one we want. There it is, access check. So now we have just one check. This is, we're interested in null pointer possibilities, and let's go and look at that. Okay, this is where we think we might have a null pointer. And perhaps the reason is that one of these variables is not initialized. Let's see, it requires that forkref of 4 is not equal to null. The question is, have we initialized all of the forkrefs? And the danger is that we forkref here, it returns null if the counter is mod 8 is equal to 0. Well, it turns out we're calling 1, 2, 3, 4, 5, 6, 7, 8 times here, and that forkref counter is going to get up to 8, and then mod 8 is going to be 0, and we're going to return a null. So CodePeer is able to simulate this code well enough to know that our 8th call on forkref is going to be a problem. It's going to return a null, and we don't want a null here. We're using the result of this in a place where we don't allow null. If we look at the declaration of person, I think that will become clearer. Let's see here. Let's look at person. Okay, so person is, there it is, not null. That's what I was expecting. So those two discriminants for when we're creating a person, these must be not null. That is, we want to have references to a fork object, and they had better but not be null references. So let's go back to where we were. And so CodePeer has simulated what would be happening, and it has identified that this is a possibility for a null reference. Okay, so I was showing you the various things over here. What I want to do now is turn on low. Now we had been ignoring low. Let's turn back on all of our various checks. And I had been ignoring low, and we actually have some low errors, but not in these two files. I have to actually rerun. There's a lot of control here, and one of the things that you can ask CodePeer to do is be pickier. So there's sort of normal level of pickiness, and then there's maximum level of pickiness. And what this turns on is the various checks having to do with floating point, underflow, and overflow. For a lot of applications, floating point isn't that interesting. There may be other kinds of checks that we suppress when you're not in maximum mode. So I'm going to go up to maximum mode because the default that we did with just the analyze all did not include all messages that are usually of less interest to some programmers. So now I'm doing my analysis with maximum pickiness, if you will, and I'm expecting now that some of these other test cases show up. Let's go to the CodePeer report, and we now have some lows here. And so we've increased the pickiness, and let's sort of drill our way down on. Now, one of the things that I've done here is I've really kind of combined two groups of tests. This was the dining philosophers example that we saw before, and we have a couple of pieces of code that are specifically designed to illustrate issues with floating point. So in particular, here we have a sum of two arbitrary floating point numbers, and sure enough, underflow can occur. Whenever you do an add or a subtract, if you aren't certain that these values are sufficiently large, there is a danger that you might lose precision. So for example, you might have an underflow where these two values are very close. This is, let's say, positive 100, and this is minus 99.99999. And if you add these two together, you can actually lose a lot of precision. You may end up with essentially just 1 bit of precision by the time you're done. You would lose all of the difference that existed. And so that's a danger when you're doing adding or subtracting, adding a number and a number very close to it in a negative sense, or subtracting two numbers that are roughly the same value. So when you turn on the picky mode, it will now find all of these kinds of possibilities of where there might be underflow and overflow. Now, not everyone wants to see all these, but there are cases where the application is very compute intensive, and cases of losing precision can be very important. So we offer the ability to detect those sorts of things very precisely. Okay, so let's look at some of these other lower priority issues here. Oh, this one we have busboy. What's busboy all about? Okay, so these are similar issues here. Floating point underflow might occur. So we're doing some computations involving floating point, and in an awful lot of cases when you do that, there is a danger of underflow. And this is one of those cases. Now, there are cases where we know it won't underflow, and let's look at that one. Let's see. So that's not very interesting. Here we go. This is a test specifically for exponentiation. And exponentiation is one way that you can get values that get too small. And for example, here, if the exponent is guaranteed to be less than 13, then we know that we will never get a result that is too small. Let's look what the base val is. The base val is 1 over 1, 2, 3, 4.5. So it's a number less than 1. So if you start taking that to a high power, you could get a very small number, and ultimately a number that underflows the range of this floating point type. But as long as we stay below 13, CodePeer is able to convince itself, well, this cannot fail. On the other hand, if the exponent can be equal to 13 or greater than or equal to 13, then we do have a possibility for underflow. And so we identify those places, but we spare you we can guarantee that this cannot go underflow. So here's a place where the range of values is helpful. It's telling us that we know in this case the exponent is in the range 0 up to 12. Well, we know it's less than 13, so that gives us the high bound. Where does the low bound of the exponent come from? Well, the low bound comes from the fact that it's declared to be of type natural, which has a low bound of 0. So coming in, this implies 0 to anything, but by the time we get here, we know we're in the range 0 to 12. So CodePeer is learning every time you do a comparison. It knows, well, if I'm in here, the comparison is true. If I'm on the then part or the else part, then the comparison is false. So it's able to use that sort of information to derive what are the possible values. Here for the exponent, it's got a value of 0 to 13, because now we've included 13. And here it's got a value of 13 up to effectively infinity. Okay, so that's demonstrating some of the new precise floating point representations.